Slope of a polar curve. Let's do this example. Find the slope of the cardioid, r equals 2 plus 2 cosine theta at theta equals pi over 6. This blue curve is the graph of r equals 2 plus 2 cosine theta. To understand the question, here's a protractor. I'm going to measure 30 degrees in standard position. So here's where 30 degrees is on the protractor. A little red mark there, 30 degrees. Move the protractor out of the way. If I draw a vector from the origin to that red dot, we have a 30-degree angle with the x-axis. It touches the cardioid at this green dot. So the question is to find the slope of the cardioid when theta is 30 degrees, meaning the slope of the tangent line to that blue curve at the green dot. Here's how we do it. Well, first of all, the slope of any curve, meaning the slope of the tangent line, is the derivative of y with respect to x, even though the equation is with polar coordinates, r's and thetas. To answer this question, we need the derivative of y with respect to x. So the y is always equal to r sine theta. This is from the definition of sine. So in this example, y is equal to 2 plus 2 cosine theta times sine theta. Y is always r sine theta. In this example, all of this is r. So y equals 2 sine theta Oh, I was going to distribute, but I changed my mind. I'm going to leave it like that. So the derivative of y with respect to theta, y is a function of theta. The derivative of y with respect to theta is the first times the derivative of the second plus the second times the derivative of the first. To underline two things here, red and green. The derivative is the first, which is red, times the derivative of the second, plus the second, which is green, times the derivative of the first. The derivative of y with respect to theta is, without parentheses, 2 cosine theta plus cosine squared theta minus sine squared theta. X is always equal to r cosine theta. This is from the definition of cosines. X is always r cosine theta. In this example, x equals 2 plus 2 cosine theta times cosine theta. X is always r cosine theta. In this example, this is r. R equals this, the equation of the cardioid. That makes the derivative of x with respect to theta the first times the derivative of the second plus the second times the derivative of the first. So I underline two things here, red and green. The derivative is the first, which is red, times the derivative of the second, plus the second, which is green, times the derivative of the first. The derivative of x with respect to theta, without parentheses, is negative 2 sine theta, negative 2 sine theta cosine theta, negative 2 sine theta cosine theta. I've just distributed green into the red over here, and this green times this red is right here. And I see like terms, so the derivative of x with respect to theta is negative 2 sine theta. Combine these like terms, that's negative 4 sine theta cosine theta. So why did we find dx d theta? And why did we find dy d theta? The answer is the original question on the slope of the curve, the slope of the cardioid. The slope of any curve is always dy dx. The derivative of y with respect to x will be the derivative of y with respect to theta over the derivative of x with respect to theta. This should look familiar because we did this when we did the parametric functions. Makes sense algebraically to divide these fractions over here on the right side. The thetas will cancel. It should be clear that this equals dy dx. This numerator, dy d theta, and I put a purple box around that. 2 cos theta plus cos squared theta minus sine squared theta. Cosine theta plus 2 cosine squared theta minus 2 sine squared theta. I want to double check that that's what dy d theta equals. Well, there's actually a mistake here because the derivative of the first times the derivative of the second, that's correct. This is the second. The derivative of the first should have a 2 there. The derivative of 2 plus 2 cosine theta is 0 minus 2 sine theta. So that should be there. And it should be, oh, I have it there. Okay, so that I think is correct. dy d theta was purple. Dx d theta, we'll make that, I think we made that blue. Dx d theta is right here. Hopefully there's no mistakes. It's negative 2 sine theta, negative 4 sine theta cosine theta. So we had y equals something with thetas. We found dy d theta using product rule. We had x equals a function of theta. We found dx d theta using the product rule. And then we need this because this is dy dx. The slope of the curve, the cardioid, that means the slope of the tangent line, at theta equals pi over 6 means this derivative when theta is pi over 6. 2 cosine pi over 6 plus 2 cosine pi over 6 squared minus 2 sine pi over 6 squared over negative 2 sine pi over 6 minus 4 sine pi over 6 cosine pi over 6. Cosine pi over 6 is 30 degrees. Cosine of pi over 6 is radical 3 over 2. The cosine of pi over 6 squared is 3/4. That's the cosine of pi over 6. So we're squaring it here. The sine of pi over 6, that means the sine of 30 degrees is a half. This says the sine of 30 degrees squared, that means a half squared. So that's 1/4. The sine of pi over 6 is 1/2. Over 4, we have the sine of pi over 6, which is a half. Next to that, we have the cosine of pi over 6, which is radical 3 over 2. 2 times radical 3 over 2 is radical 3. 2 times 3/4 is 6/4, which is 3/2. Negative 2 times a fourth is negative 2/4, and negative a half. Negative 2 times a half is negative 1. And this over here, there's a 4 in the denominator, it cancels with 4 there, so we just get radical 3. This 4 and the 4 down there cancel. This equals radical 3. 3/2 minus a half is 2/2, which is 1. Negative 1 minus the rest on the bottom. So these are the numerator and denominator here are called opposites. Anything divided by the opposite is equal to negative 1. That's the answer. That's the slope of the cardioid. Negative 1 is the slope of the cardioid. Cardioid at pi over 6. Let me get back to the original picture. We draw a tangent line to this cardioid at that green dot. The tangent line has slope negative 1.